figure below shows a block of mass m1 on a frictionless inclined plane of elevation theta connected to a free to rotate cylindrical pulley, so this one, rotational inertia I equaling half mr squared, and another block of mass m2. The question asks us to calculate the linear acceleration of the system as shown below. So I have drawn a small little system to help visualize the problem. So over here, we have a typical inclined plane. It's frictionless, so that's also a good thing for us, less work. Angle of elevation theta over here. Here's block M1 on the frictionless plane. Here's M2 suspended by the free to rotate pulley. Now be careful here. The problem says that this is a free to rotate pulley. Therefore, it's not going to be as simple as we expect. We will actually have to create 3 Newton law equations instead of 2, because there is a torque force generated by this free to rotate pulley, which is not usually there in a static pulley. Okay, so let's first draw some free body diagrams on this guy. Okay, so first of all, let's think about the direction of motion. So it'll go downwards like this way. So we have on M2, there is a weight force acting downwards, which I'll call W, which is the mass times the gravitational constant. So the mass is M2 multiplied by the gravitational constant, which is G. Okay, there is also a tension force acting up. Now be careful here again, because it's a free to rotate pulley, the tension over here, which I'll call T2 because I'm referring to this one as M2, is going to be different from the tension up here, which I'll call T1. So this is also something you have to be careful about. Okay, the weight of gravity acts downwards on M1 like this. However, we should resolve it into its components to see how much of the gravitational force is going to act parallel to the incline. Okay, so let's draw a line over here perpendicular to the incline and one parallel to the incline. This is our angle theta. This here is the weight M1G, sorry. Now let's look at this. The one perpendicular to it will be mg times cosine theta. M1G cosine theta. Now, acting parallel to the pulley, which is the component that we actually are concerned with, is M1G sine theta as such. So we can say that the direction of motion here, just to make it a bit more clear, is M1G sine theta. Now, because it's a frictionless pulley again, we do not have to really be bothered about this component over here. However, if there was friction, the frictional force would be equal to some constant mu. So mu k multiplied by the normal force, which is M1G cosine theta. Okay, and finally, let us consider the actual pulley itself. So on the pulley itself, there is going to be a tension force, which is pulling it this way, and a tension force pulling it that way. There's also the normal force with respect to the axle, which I'll just call Fn axle, but we won't be too concerned about that. Also, along with the weight force, which I'll call Fg of pulley. Okay, so this is a bit of a mess right now. Let us now create 3 Newton laws equations to solve for 3 unknowns: the acceleration, the tension on T1 and tension on T2, and we'll treat everything else as a constant. So let's start with the basic Newton laws that we should probably get off right away, which is the Newton law for M1, the Newton law for M2. So let me write it as here in pink. Number 1. So for M1, as we said before, the system of the pulley is going to be acting downwards like this. So this M1 block over here is going to be pulled up the incline. Hence, the tension force is going to outweigh the gravitational force acting downwards. Or in other words, T1 minus M1G sine theta is equal to mass of 1 times the linear acceleration. Okay, so same thing, let's do this for block 2. Again, because the system is falling downwards, in this case, the weight force is going to outweigh the tension force acting upwards on the block. Or in other words, M2G minus T2 is equal to M2A. Okay, that will be pretty useful to us. However, we have three unknowns here in two equations. What are the unknowns? Unknowns are A, the linear acceleration, which is the problem that we're trying to get. We also have T1 and T2. Unlike a static pulley, the tension are different. Therefore, we need one final equation that links the tension forces together. We will then have three equations and three unknowns, and just a basic simultaneous equation. Okay, whoops, my bad. Let's look on the pulley over here. The pulley generates a torque force, so torque here. Torque is also the same thing as saying the rotational inertia I multiplied by the angular acceleration alpha. Now, what is I? Well, in last week's video, I showed in a part A, part B sort of video, how the rotational inertia of a cylinder is half mr squared. If you would like to know the derivation of that, I please encourage you to watch that video. However, the question kindly gives us the rotational inertia right over here, half mr squared. So we will use that in this problem. Again, I won't go to the derivation here. I went through a last video if you would like to see that. So we'll just fill in that for I. Half capital M R squared. I'll just say capital M to differentiate between M1 and M2, and it's clear. And this is all multiplied by alpha. Now note that torque, the definition of torque, is equal to the force multiplied by R, the length. Okay, now what is our force? Well, we have two forces here. We have T1 and T2. However, T2 acts in the downwards direction, the way we're concerned with, and T1 acts in the opposite direction. So this is the same thing as saying, which I'll just write over here, T2 times the R minus T1 times R. Okay, now let me just get rid of this part first. Let me give myself a bit more space. We also know that alpha is equal to the linear acceleration over the radius. So over here, there's some really nice canceling outs. Let's just write this again. Half capital M R squared times alpha, which is A over R, is equal to T2 minus T1 multiplied by R. All I'm doing is I'm just factoring out the R in this part of the equation. Now over here, what I can do is I can cancel out one of the R's here and one of the R's here. So I get half MR times A over R is T2 minus T1. And notice I can also cancel out this R. So I've completely got rid of the R variable, which is great. So writing this all out in full, I get half MA is equal to T2 minus T1. And that is our final equation. And now we have three good equations to solve for three unknowns. So let us do that. Let me just rewrite the first two equations over here. One was T1 minus M1G sine theta will equal to M1A. And for equation 2, it was M2G minus T2 is equal to M2A. Now notice I have T2 minus T1 is equal to half MA. So let me get rid of the tension variables. So in other words, T1 can be written as T1 is equal to M1G sine theta plus M1A, which is now great because now we can get rid of the T1. Likewise, we can do this for T2. T2 will be equal to M2G minus M2A. Sorry, let me just write this a bit clearer. There we go. And now notice I can get rid of them by subtracting T2 from T1 and saying they're equal to half MA. So T2 minus T1 will equal to M2G minus M2A minus M1G sine theta plus M1A. Okay, so let me just expand the brackets. We'll get M2G minus M2A, which is T2, minus M1G sine theta minus M1A. And what is this equal to? Well, this is equal to half MA. Now this is finally great. We have one equation with only one unknown. So this is basically a simple linear equation that we can just solve using basic algebra. Let us bring all the A variables to one side. Okay, I'll now do this in blue just to make sure that we've got our final equation here in pink. I'll now do the rest in blue. Let us bring this variable and this variable all the way to the other side. We'll get that half MA plus M2A plus M1A is equal to M2G minus M1G sine theta. Okay, now let us factor out the A on the left-hand side and factor out the G on the right-hand side. I'll get that A half M plus M2 plus M1 is equal to G M2 minus M1 sine theta as such. Now, I don't really like the fraction, so a simple way to get rid of it is just to multiply by 2 on both sides of the equation. So what will I get at the end of that? Well, if I multiply by 2 throughout, I'll get A times M plus 2M2 plus 2M1. I don't really like the way that M2 and M1 are written, so I can just swap them. So I'll just do that. And that will equal to, sorry, my bad. 2G times M2 minus M1 sine theta. Now, this is great. We just have one final step to solve for acceleration, and it's just to divide by this business over here. So finally, we get that A is equal to 2G M2 minus M1 sine theta over M plus 2M1 plus 2M2. And that right there is our final answer. So as you can see, this is a much different process than if we had a static pulley. And in all fairness, we didn't take this pulley without slipping. If the pulley were to slip, it would be much more complicated. But for this question, we specifically assumed that it did not slip. So, but as you can see, instead of having two unknowns as usual, like just normal two-dimensional kinematics, we now had to take into consideration an extra torque force. So, which made the question a lot more harder, but I hope that wasn't too hard to understand. And we did eventually get a nice, well, I guess, sort of nice expression for A. Thank you.